Hello everyone, welcome to this session. In this session, we are going to discuss Laplace transform of Heaviside unit step function. In our previous session, we have discussed Laplace transform of periodic function and some examples. In this session, we focus on definition of Heaviside function, shifted Heaviside function and Laplace transform of Heaviside function, second shifting theorem and some examples. First of all, let us see definition of unit step function. Here Heaviside unit step function, Heaviside function or unit step function is defined as u of t equal to 0 for t is less than 0, 1 for t is greater than or equal to 0. If we see this graph, in this graph on x-axis, I have taken this t and on y-axis this unit step function u of t. Then you can observe here when t is less than 0, this function u of t is 0. So on left hand side, we don't find any graph. Here on right hand side of this y-axis, here value of u of t is 1 for any value of t. For t is greater than or equal to 0, that means for t equal to 1, 2, 3, so on up to infinity, value of u of t is only 1. That's why here you can observe a straight line which is parallel to x-axis. So this is definition of unit step function. Now Laplace transform. To find Laplace transform of unit step function, first let us consider basic definition of Laplace transform, that is L of f of t equal to integral 0 to infinity e power minus st f of t dt. Now in the place of f of t, write this unit step function u of t. Then we get L of u of t, Laplace transform of u of t equal to integral 0 to infinity e power minus st u of t dt, which is equal to integral 0 to infinity e power minus st into 1 dt, because when t is greater than or equal to 0, that means from 0 to infinity, value of this unit step function is 1. That's why here I have replaced u of t by 1. Now integrate this e power minus st. So integration of e power minus st is e power minus st upon minus s under the limit 0 to infinity. When we apply upper limit, we get e power minus infinity by minus s minus, when you apply lower limit, you get e power 0 upon minus s. As e power minus infinity is 0 and e power 0 is 1, here first term becomes 0 and this second term gives 1 upon s. So Laplace transform of unit step function u of t equal to 1 by s. Now let us see next definition, shifted Heaviside function or shifted unit step function. Here this is the Heaviside function shifted a units to the right. What does it mean? You can define this as u of t minus a equal to 0 for t is less than a, 1 for t is greater than or equal to a. When you observe this graph, here this line, straight line, which is parallel to this x-axis is shifted a units to the right. So here this is graph of shifted Heaviside function. Here this is a on x-axis. So you can observe there is no any graph on left hand side of a. That means when t is less than a. When t is greater than a, again we get a line which is parallel to this x-axis at u of t minus a equal to 1. Okay, so this is shifted Heaviside function. Now u of t minus a, this shifted Heaviside function can be used to turn a signal off until time t equal to a. That means if you want to on any washing machine, any machine, if you want to on that machine at a particular time, then you can fix or you can adjust the time before. That means just like alarm clock, just like a alarm, you can set that time using one circuit. Okay, in such circuits, if you convert that concept into mathematical form, you can find this unit step, shifted unit step function. So shifted unit step function, this concept is useful in signals and systems where we want to turn a signal off until time t equal to a. Okay, and then to turn it on. So in those, when you deal with such circuits, so in mathematical formation, you need this shifted Heaviside function. Now let us see next definition, Laplace transform of shifted unit step function. Let us see Laplace transform of this shifted Heaviside function. So L of u of t minus a, Laplace transform of u of t minus a equal to e power minus as upon s. How do you get this? As usual, first we have to consider basic definition of Laplace transform, then replace this f of t by shifted Heaviside function. Now here we have replaced f of t on both sides of this equation by shifted Heaviside function. Then according to definition of shifted Heaviside function, u of t minus a, here u of t minus a equal to 0 when t is less than a and 1 when t is greater than or equal to a. This is definition of shifted Heaviside function. So we can split this integral 0 to infinity as 0 to a and a to infinity. So in the interval 0 to a, that means when t is less than a, value of this function is 0. That's why here I have written 0. Here u of t minus a is 1 when t is greater than or equal to a. So here you can write 1 in the place of u of t minus a. Now first integral becomes 0. Now when you integrate this one, we get e power minus st upon minus s under the limits a to infinity. Now when you put upper limit, this value of this expression is 0. When you apply lower limit, you get e power minus as upon s. So here e power minus as upon s is Laplace transform of u of t minus a. Now when you multiply this u of t minus a by some function f of t, then this function is unchanged for t is greater than or equal to a, but it is replaced by 0 for t is less than a. That means you can define u of t minus a into f of t as 0 for t is less than a and f of t for t is greater than or equal to a. Now the function u of t minus a, f of t minus a represents the graph of f of t shifted through a distance a to the right. You can understand these definitions by some graphs which I have plotted. Let us see those graphs. Here this graph, this has been cut up to t equal to 3 by 2 here. That means here we don't find the graph which is existing on negative x-axis. Okay, so here u of t minus a into f of t means this, the graph or the function f of t exists only from t equal to a. So here you can observe this graph only starting from t equal to 3 by 2. Okay, so this is graph of u of t minus 3 by 2 into t sin t. But when you observe this graph, this is u of t minus 4 into t minus 4 sin t minus 4. That is, this is u of t minus a, f of t minus a form. Then here this graph starts from this t equal to 4, but this whole graph is shifted 4 units to the right. Okay, so you can understand the definitions which we have discussed in previous slide using this graph. Now we can define second shifting property as if L of f of t equal to f of s, then L of u of t minus a, f of t minus a equal to e power minus as f of s. We can derive this using basic definition of Laplace transform. replace f of t by u of t minus a into f of t minus a. Then we get this step. Laplace transform of u of t minus a f of t minus a equal to integral 0 to infinity e power minus st into u of t minus a f of t minus a dt. Now according to definition of u of t minus a, u of t minus a is 0 when t is less than a, and this is equal to 1 when t is greater than a. So first we can split this integral into two integrals. Integral 0 to a, this integrand dt, plus integral a to infinity, this integrand dt. But when interval is 0 to a, value of this u of t minus a, unit step function, is 0. So here we got 0. Now here its value is 1. So we get integral a to infinity e power minus st f of t minus a into 1 dt. Now first integral becomes 0 if we integrate this second one. But before integration, we have to take one assumption. Let this t minus a equal to p. Then by integrating on both sides, we get dt equal to dp. Then here t equal to, we have to convert even limits. When t equal to a, p becomes 0. When t equal to infinity, p also becomes infinity. So here we get integral 0 to infinity e power minus s into t means p plus a. So here s into p plus a into f of p dp. E power minus sa is constant, so we have taken it out. Integral 0 to infinity, here e power minus sp remains into f of p dp. This is just similar to basic definition of Laplace transform, but in the place of t, you can find p. So here you can write e power minus as f of s, where f of s is L of f of t. Now, you can define this second shifting property in this way also. If L of f of t equal to f of s, then L of capital F of t equal to e power minus as f of s, where this capital F of t is defined as f of t minus a for t is greater than a and 0 for t is less than a. Even you can find Laplace transform of this by using same procedure, whatever we have discussed now. Here replace this small f of t by capital F of t. Again split this integral into two integrals, integral 0 to a and integral a to infinity. So according to this definition, when t is less than a, that means when this integral is from 0 to a, value of this capital F of t is 0. So first integral disappears, and here in the second integral, here interval is from a to infinity, then value of f of t, capital F of t is small f of t minus a. So here we get integral a to infinity e power minus st into, in the place of f of t, you can find f of t minus a dt. Again, to evaluate this integral, we are using same procedure. That means we have taken t minus a equal to p, then dt equal to dp. Then here p becomes 0 to infinity. Then this integral can be written as integral 0 to infinity. Here this is 0. Integral 0 to infinity e power minus s into p plus a into f of p dp. That is e power minus sa into integral 0 to infinity e power minus sp f of p dp. That is e power minus sa f of s. So here both these forms, you can consider this form or this form, but Laplace transform is same, e power minus as f of s. This is called second shifting property. Then let us see some examples based on these definitions. Now here we have discussed unit step function, definition of unit step function, Laplace transform of unit step function, that is 1 by s, L of u power t equal to 1 by s. Then shifted Heaviside function, that is u of t minus a, this is definition of u of t minus a, and Laplace transform of u of t minus a is e power minus as upon s. Then we have discussed unit step function. Okay, and second shifting property. So second shifting property we have discussed or we have defined in two ways. This is one way of defining the second shifting property. This is other way. So you can find any form in your final examination question paper. So here even if you find L of u of t minus a, f of t minus a, or L of capital F of t, but its Laplace transform is same, e power minus as f of s. Now let us see some examples. First example is find L of f of t, where f of t equal to sin t minus pi by 3 for t is greater than pi by 3, 0 for t is less than pi by 3. And here I have listed some 7 examples. Let us see one by one. Now here first example is this one, and let us write definition first. L of f of t equal to f of s. If L of f of t equal to f of s, then L of capital F of t equal to e power minus as f of s, where capital F of t equal to f of t minus a for t is greater than a, 0 for t is less than a. Here capital F of t is given, that's why we have considered second shifting property in this form. Now compare these two. F of t minus a equal to sin t minus pi by 3, that means a equal to pi by 3, right? So f of t minus pi by 3 equal to sin t minus pi by 3. In the place of f of t minus pi by 3, here sin t minus pi by 3 is given. So from this equation you can write f of t. If you replace t minus pi by 3 by t, then you get f of t equal to sin t. Then we can find f of s. F of s is nothing but L of f of t. So L of f of t equal to Laplace transform of f of t means sin t. So Laplace transform of sin t. So by its definition, by the definition of Laplace transform of sin a t, you get 1 by s square plus a square. That is 1. A by s square plus a square, that is 1 by s square plus 1. Hence here L of capital F of t equal to e power minus as f of s. This is second shifting property. According to this, here e power, a means pi by 3, so e power minus pi by 3 into s into f of s means 1 by s square plus 1. So this gives e power minus pi by 3s upon s square plus 1. Now see next example. Find Laplace transform of f of t, where f of t equal to t minus 1 whole square when t is greater than 1 and 0 when t is less than 1. So here f of t minus a equal to t minus 1 whole square, that is a equal to 1. Compare these two, a equal to 1, and f of t minus 1 equal to t minus 1 whole square implies f of t equal to t square. Now find Laplace transform of f of t, that is t square. Then according to this definition, Laplace transform of t power n equal to gamma n plus 1 by s power n plus 1 or n factorial by s power n plus 1. So here you get 2 factorial by s power 2 plus 1, that is 3. 2 factorial is 2, so we get 2 by s cube. This is f of s. According to definition of second shifting property, we get L of capital F of t equal to e power minus as f of s, that is e power minus 1 into s into 2 by s cube, which gives 2 into e power minus s upon s cube. This is Laplace transform of f of t, where f of t is in this manner. Now let us see third example. Find Laplace transform of t minus 1 whole square u of t minus 1. If you observe this, this is in the form of Laplace transform of u of t minus a f of t minus a. Okay. So Laplace transform of this is e power minus as f of s according to second shifting property. So let us consider given function first. Here f of t minus a is t minus 1 whole square. Here if you compare these two, in the place of f of t minus a, you can find t minus 1 whole square. So f of t equal to t square. Then Laplace transform of this f of t is Laplace transform of t square, that is 2 by s cube, n factorial by s power n plus 1, that is 2 by s cube, which is equal to f of s. Now f of t minus a is nothing but t minus 1 whole square. that is f of t minus 1, which is t minus 1 whole square. Here a equal to 1. So Laplace transform of t minus 1 whole square u of t minus 1 can be written as e power minus as f of s according to definition of second shifting property. So replace a by 1. That means in the place of a put 1 and in the place of f of s write 2 by s cube. So here you get e power minus 1 into s into 2 by s cube, that is 2 into e power minus s upon s cube. This is Laplace transform of t minus 1 whole square u of t minus 1. Let us see next example. Find Laplace transform of sin t into u of t minus pi by 2. Here if you observe, this is in the form of u of t minus a, but sin t is not in the form of f of t minus a. So first we have to convert this sin t in the form of sin t minus a. So here L of sin t into u of t minus pi by 2. Here sin t can be written as sin t minus pi by 2 plus pi by 2. I have added and subtracted pi by 2 because here in the place of a, pi by 2 is given. Okay. Now here you can use sin 90 plus theta formula. Sin pi by 2 plus theta is cos theta. So here you get cos of t minus pi by 2. T minus pi by 2 is theta. Here pi by 2 plus theta. Sin pi by 2 plus theta equal to cos theta. So we get cos t minus pi by 2. So u of t minus pi by 2 is as it is, no change. Now compare this with f of t minus a. F of t minus a equal to f cos t minus pi by 2, that is f of t minus pi by 2. Okay, then f of t is cos t. F of t becomes cos t because in the place of t minus pi by 2, if you write t, what do you get? F of t equal to cos t. Now find Laplace transform of this. So Laplace transform of f of t equal to Laplace transform of cos t, which is equal to s by s square plus 1, which is equal to f of s. Okay. So now according to second shifting property, here we get e power minus as into f of s. Here a means pi by 2. F of s means s by s square plus 1. If you write those expressions here, you get e power minus pi by 2s into s by s square plus 1, which gives s into e power minus pi by 2s upon s square plus 1. This is Laplace transform of sin t u of t minus pi by